Okay. Good afternoon. Okay. So we continue to talk about special distributions. For the distribution that we discussed in this chapter or in other chapters, basically what you need to know is, first of all, what does the random variable represent? So far we discussed about Bernoulli discrete uniform distribution, Bernoulli distribution, binomial distribution, negative binomial distribution, and a bit on Poisson distribution. So each distribution, have their own has their own meaning for the random variable. So, for example, for binomial distribution, we're talking about the random variable representing the number of successes in n Bernoulli experiments or n trials, all right, n independent trials. While for negative binomial, the random variable x represents this time not the number of successes but the number of trials that you need in order to have k successes, and each trial has only two outcomes. While for Poisson distribution, the x also represents the number of successes, but this time it's not the number of successes within n trials, but instead it is the number of successes over a region or an interval. So maybe an interval of time, maybe an interval of distance. All right. So you have to know what the random variable represents. What does the random variable x represent for a particular distribution? And then you also have to know what the probability function, the form of the probability functions looks like, and for the range of the x for which the probability function takes that form. All right. Of course, you have to know how to compute the probability based on the given density probability function, and also you have to know what is the expectation of x and also the variance of x. All right. So here the Poisson distribution, the probability function is defined as e to the power minus lambda times lambda to the power x over x factorial. And this form valid for x equals 0, 1, 2 up to infinity. All right. Now, all these probability functions should depend on some constants. And this constant will identify or characterize the behavior of the distribution. So for Poisson distribution, there are only one such constant. It is the lambda. Okay, of course, you also have to ask, what is this lambda? So usually we try to link up this unknown or this constant, or we call it parameters, to the expectation of x or the variance of x. So for Poisson distribution, lambda, the parameter lambda here is the expectation of x, so that we can link this together. All right, so the lambda in the probability function is the expectation of x. Okay, so let's look at some. So this is the expectation of x if x follow Poisson distribution. All right, and here's some to show you how to obtain or how to derive this expectation. So you may spend some time to look at or understand it, but one technique that we used here, or in fact two. First of all, instead of work out directly expectation of x squared, all right, this expectation of x squared, this expectation of x squared, which is difficult to get. So instead we work on expectation of x times x minus 1. The reason why we do that is that this will help us to simplify our summation. because x times x minus 1 can cancel two of the factors of x factorial in the denominator, because x factorial means x times x minus 1 times x minus 2 up to 1. So we can do some cancellation. The second technique that involved in computing all this is that we make use of the property that the sum of the PDF is equal to, or probability function is equal to 1. The sum of the probability function equal to 1. So in this case, we try to rearrange this, all right, in such a way that it becomes like that. It's just by assuming y equal to x minus 2. Then this y obviously becomes a random variable. This whole summation sign, a summation is worked on this term. And this term looks as if it is the probability function of a Poisson distribution with parameter lambda. And we sum up from 0 to infinity. So this is equal to 1. So that's how we calculate the expectation of x times x minus 1. All right? Okay, so now let's look at some examples. So let's look at example 1. So suppose the average number of robberies in a day is 4 in a certain big city. So we are asked, what is the probability that 6 robberies occurring in 2 days? All right? Now, okay, so in this case, you think of it, it is not the number of trials that we're interested, but it is over a period of time. All right? So it's over a period of 2 days. 2 days. All right? So within these 2 days, you ask yourself, what we want is the number of occurrence, and this occurrence is the robberies. So we are asked how many number of occurrence within this period of 2 days. All right. So we can let this x be the number of robberies, and the question basically asks, what is the probability of x equal to 6? All right. So you must define clearly what the x, the random variable x means. In this case, it's the number of robberies. I'm sorry, I missed one important. In 2 days. All right? In 2 days. Because the period that we're interested in is 2 days. All right? So this is the interval that we're interested in. So, of course, then we ask, what is the distribution of x? So that we can compute this probability. So it's something to do with the number of successes or number of occurrence over interval. So it's likely that we can model it by Poisson distribution. So it's x follow a Poisson distribution. Poisson distribution. All right? Then the next question is, what is the parameter lambda? What is the lambda? Right. Remember, lambda is the expectation of x in this interval. So, in this case, we know that for a day, the expect occurrence is 8. So in 2 days, the number of robberies that we expect should be 2 times 4. Or in other words, 8. So now we have everything. We know that this random variable x is the number of robberies in 2 days, and we expect the number of robberies in 2 days is 8. Okay, so we are asked to find the probability of x equal to 6. All right, so here it is. So the answer is 0.122. All right. So we can also okay, just in case you don't have your computer or a very powerful calculator to do it. So in statistics, in all most of the statistical books, introduction to statistics, they may have this kind of tables, or even they don't have it. Don't worry about it. If they need, I will be provided with these tables. Okay, but I just share with you how to use this table to present the probabilities. So in this case, you can see that there's a lambda. So lambda is the column heading. So the third row, okay? So this lambda equal to 1. lambda equal to 2, lambda equal to 3, and so on. So our example, we need lambda equal to 8. So we look at this lambda equal to 8, and then this represents the x value. And in fact, it says lower tail probability of Poisson. Lower tail means the lower tail means the left-hand tails. Okay, or you can say it's probability of the random variable x less or equal to certain constant. All right, this one, x, this part. All right. Okay, so it's this part. All right. So what does it mean? It means that for x less or equal to 6, with lambda equal to 8, then it is 0.313. So this number represents the probability of a random variable x less or equal to 6. This number. Let me highlight it. This number means that it's the probability of the random variable x less or equal to 6 when x follow a Poisson distribution with parameter 8. All right. So the next one, this one, is the probability of x less or equal to 7. So now, if I want to have probability of x, all right, less or equal to 7, then it will be the difference of the two. All right. You have to know that probability of x less or equal to 7 minus the probability of x less or equal to 6. Then what's the answer? The answer is probability of x equal to 7. All right. So what I just said is that, okay, if you want probability of x, in fact what I highlight is, okay, if I want probability of 6, then this should equal probability of x less or equal to 6 minus probability of x less or equal to 5. All right. The two that I just highlight is not for this answer, but probability of x equal to 6 means the difference between these two. All right. So, of course, you can just use this e to the power minus lambda to the power 8 over x factorial. 6 factorial. Well, lambda equal to 8, so I replace it by 8. So to calculate the probability. So alternatively, I can use this. It's the same thing as just what we did, but this time we consider the probability greater or equal to certain value. All right. So this is how we get the answer. All right. Okay. Example 2. So you can see that all are given you, all questions or examples up to this point. It gives you the average number of what happening, the oil tanker arriving, the arrival of the oil tanker. So the number of the oil tankers arrive at the port, and each day their average is 10. So sometimes more, sometimes less. So, but the facilities of the port can handle only 15 tankers per day. So you're asked, what's the chance that on a given day, tankers will have to stand away? All right, so you have to translate this question into a probability statement involving x, where x is the first of all, x is the number of tankers arrive on a given day, on a particular day. All right, I want you to understand x is the number of tankers arrival, but this is not good enough to describe the random variable x. You also have to mention that this is the number of tankers arrived on a day, on a given day. So you specify the period. Otherwise, all right, we're talking about different things if you're talking about different periods. So one may refer to one day, the number of tankers arrive on a given day, or the number of tankers arrive in a given week, or a number of tankers arrive in a given month. So in this case, in all these cases, there are different periods. So we specify that the period that we're talking about is 1 day. So then what is the distribution of X? Because it's the number of occurrence in a particular interval, so this follows a Poisson distribution with a parameter lambda. So what is lambda? So it's an average. Lambda equal to expectation of X. In this case, it's 10. So, or we can say that X follow a Poisson with parameter 10. Then, send them away. So if the number of tankers arrive is 1, no need to turn it away. 10 tankers arrive on a day, it's okay. We still can manage. 15 is the largest number that we can handle. Once the number of arrivals greater than 15, then sorry, we cannot handle, and so we have to send them away. So basically, you are asked to compute this probability. All right. So I want you to first of all understand the problem, what you are supposed to find, get the random variable, and explain what this random variable means. Then what is the distribution of this random variable? And for the distribution, you need to know, very crucial, the parameter. So for Poisson, it's easy. The parameter is just expectation of X. So expectation of X over that interval. All right, so here it is. So we work it out. Okay, obviously, if without the table where someone have done it for you, wow, how do I add infinite number of terms? All right, so we will not do that. Instead, we take the complement, 1 minus, okay? So in other words, we change this to 1 minus probability of X less or equal to 15. So in this one, that at most 16 terms. Don't forget, X start from 0. Probability of X equal to 0. There will be maybe no tankers arrive on a given day. So we work it out. It is 0.0487. All right? So, in other words, there are about 5% of the time, we interpret 5% of the time that you may turn away some of the tankers. So if you don't want to lose these customers, then you just have to increase your facility so that you can handle more, all right? More of the tankers. All right? You see? Okay. So I want probability X. Yeah. Oh. 15. I don't have 15 here. Too bad. So alternatively, if I have a table that gives me the cumulative probability on the right-hand side, then this one is equal to this, and then I can read out directly from the table. All right? Okay, now you can create the table yourself in Excel. So just use this command. So this is the command. Okay. First of all, you need an equal sign to tell the computer, to tell the Excel that you are going to compute something. Equal means that you want to compute something. So this is the function, Poisson.dst. Poisson distribution. This is the X. This is the lambda. And this one is either true or false. All right? If you want to compute the probability, okay, if X follow Poisson, let's say with parameter, what is the parameter that we work on? 10, right? Oh, 10. Oh, I have 10 here. All right? Anyway, okay, so it's 10. So, and I want to compute the probability of x, all right, less or equal to 15. Then I just use this 15, right? This is x, and the mean is 10. Cumulative, so this is true. Then that will give you this probability. But this is not I want. I want probability of x greater than 15. So what I have to do, I have to put the 1 minus in front. 1 minus this whole thing. Then that will give me the answer. All right, so that's how you can use Excel to do it. Of course, for those who know R, you can also use R to compute. The most important question, will this be test or examined, right? Your most concern, right? It's for your own good to compute it instead of, so in the exam, no specific questions will be set on how to use the Excel, all right? But you better know one way to do it. Either use Excel, use R, or some other ways to get the answer. All right? You won't want to compute adding infinite number of terms, right? Or adding 16 terms. So you want to have some way to do it if possible. So use the software. Excel is available for most of the computers, so you can do it. A very minor point about this command. My experience is that some Office, I don't know which version, maybe 2013 or 2010, they may use comma instead of semicolon. So if the semicolon that separates these arguments does not work, replace it by comma. Replace it by comma, all right, to separate the arguments. And don't forget to put the equal sign. Without the equal sign, then they won't compute it. Treat it as a text. All right, so remember to put the equal sign. All right, so, okay, so we have this example 3. So we have this breakdowns for shift, 8-hour shift, all right? And average number, the number of breakdowns per this shift with a mean 1.5. And what is the probability exact 2 breaks down during the midnight shift? Hey, midnight shift, huh? What is the expected number of breakdown for a midnight shift? Is it 1.5? Why is it 1.5? Is it 1.5? Do you believe that it's 1.5? Yes, right? Thank you. Okay, let me put it this way. You may argue, okay, midnight shift, this will tire or whatever may be different, right? But we don't make it so complicated. So we assume every shift, every 8-hour shift, whether it's morning, afternoon, or midnight, all right, they will have the same number of mean breakdown, all right? But in real life, you may consider differently. But for this example, we assume that they're the same. So therefore, for this midnight shift, the expected number of breakdowns is still 1.5. 1.5. And how can 1.5 breakdowns occur? Hey, it's either no breakdown, 1 breakdown, 2 breakdown. Why is it 1.5? Something wrong? Why? Why 1.5? Why? I can see 0 breakdown on that shift. 1 breakdown, 2 breakdown. The point is, this is the mean breakdown, the average number of breakdowns. So sometimes 0, sometimes 1, sometimes 2, sometimes it will be 5 breakdowns. But then we take average of all the shifts, and then the average is 1.5. All right? Okay, another question. Fewer than 2 breakdowns during the afternoon shift. All right? And what is the probability that no breakdown during the 3 consecutive 8-hour shift? So here, we assume that the machines operate independently. Okay? And why we need that, I will explain it in a minute. All right? Okay, so now, it's a period of time, 8 hours, 8 hours. X is the number of breakdowns in an 8-hour shift. All right? Breakdown, number of breakdowns in a shift, 8-hour shift. All right? That is my X. Then next question, what is the distribution? So X supposed to be number of occurrence, so it follow a Poisson distribution, and with the mean equal to 1.5. All right? So the first question is probability of X equal to 2. The second question is probability of X fewer than 2. Means what? Less or less equal? Can it be equal? No, Is it? Is that what we asked? Huh? Yes, thank you. I need your answer, right? I'm not as confident as you are, right? So I need someone to support my answer, right? Just like you always ask, hey, is this the answer? Right? Okay, then what is the probability that no breakdown during the 3 consecutive 8-hour shift? Okay, now here there are 2 ways to do it. One is based on the events. We want event A is no breakdown in the first shift. Event B, no breakdown in the second shift. Event C, no breakdown in the third shift. I want all this to occur. That means A intersect B intersect C. So this one equal to the product of, okay, so if A is the event that no occurrence, no breakdown in the first shift, B and C, second and third shift, no breakdown. So we want the probability of this. So because they're independent, so it's equal to probability of A, probability of B times probability of C. Remember, this requires A, B, C are independent events. So what is probability of A? So we work it out. B and C are similar, so it just raised to power 3. This and this and this, these all are the same. All right? All right? Because it doesn't matter whether it is first, second, or third shift. They are just one shift of 8 hours, and we assume that the average is 1.5. So that's one way to look at this problem. I mentioned the second way. So what is the second way to handle this problem? So we look at it as, all right, we have 3 shifts. So each shift as one trial. And in this trial, there are only 2 possible outcomes. Either a success or a failure. And what is a success in this shift? If there's no breakdown, we consider it success. No failure means that, if there's some breakdown, then that means a failure. So basically, I formulate question C into a situation where I have 3 trials. Each trial has only 2 outcomes, either success or failure. Success means no breakdown. If more than one, if there are 1 or more breakdowns, then there's failure. So we break it down into a binomial situation, but we can describe it by binomial distribution. All right. So you can think of it. It is y, which follow a binomial distribution with n equal to 3, and then the probability of a success. That means no breakdown. We have not worked it out. So it's one of these probability. All right. So what we are asked is the probability of y equal to what? No breakdowns during the 3 consecutive. So I want to compute probability of y equal to what? 0, 1, 2, 3, 4, 5, 6. 0, right? Right? Sure? Y equal to 1 means what? What, at least one. Y equal to 1. That means 1, exactly 1. One shift among the 3 shifts have no breakdown. So the others, they have breakdowns. Because Y equal 1. Okay? So I want all 3 shifts have no breakdown. So it means what? Y equal to what? 0. Y equals 0. Y equals 0, that means no. So look at this first shift, second shift. All are failures. Failure means what? Breakdowns here. Then it's considered failure. Right? So, is it? I wrote down Y equals. I just wonder why. Okay. Yeah, there's 0, but not here. The answer is Y equals 3. Right? You want to see there have 3 trials, 3 shifts. I want the first shift, no breakdown. That means a success. I want the second one a success, the third one a success. I need 3 successes out of 3 trials. All right, so Y equals 3. That's what we want to find. All right? So that's another way to look at it. I formulate it, I create a new random variable called Y, which to model what I want. I want to find how many successes out of these 3 shifts. Success means no breakdown. All right, so then you can work out easily. So this is probability x equal to 2 for part A. For part B, probability x less than 2. All right, so these are straightforward. This one not too difficult to calculate, or you can use your calculator to do it easily. Okay, the third one, as I said, you need to calculate this. Remember I say Y follow a binomial with n equals 3, and this P referring to the probability of x equal to 0. No breakdown. No breakdown. What's the chance? No breakdown. So that works out to be 0.2231. So this is 0.2231. All right? So this is binomial, n equals 3 and p equal to 0.2231. And we want all 3 trials, all 3 shifts have no breakdown. So y equals 3. And you just have to remember, when you say no breakdown, does not mean that always 0, 0, 0. You must know what does y mean. The y is not no breakdown, but y is the number of shifts that have no breakdown. All right? It's not 0. Okay. Example 4. Example 4 is typically is not working on an interval, but instead working on we're working on a door, a wooden door, whether the quality is good or not. So we look at it, and for average of 1 square foot of the door, there's 0.5 minor fault. So that means we're talking about occurrence of minor faults. So look at the door, all right. On average, 1 square foot of the door, we can have 0.5 minor fault. So for a door, if the door is very huge, let's say it's 3 meter, or 1 square foot, 1 by 1. So a door may be 10 square feet, all right, 10 square feet, 2 by 5, 3 by maybe 12 square feet. So the whole door, all right, depends on the size or the area, and then we work out the average fault, minor faults on that door. All right. So subsequently, 1 square foot of each door surface was examined, and the owner decides to have all doors revert when they find that 2 or more minor faults in a square foot of surface being inspected. All right. So what is the probability that a door will fail inspection and sent back for reworking? All right. And what is the probability the door will pass the inspection? So you have, first of all, decide or define a random variable. And what does it mean? What is the distribution? And then link up all these questions, find the probability, to the random variable. All right. So here, we are not looking at the whole door. We just look at a particular area, 1 square foot of the door. Okay. Then expect x equal to 0.5. So we are asked, what is the chance that it is greater or equal to 2? Because once you find 2 or more, then you need to, we consider it fail the inspection and then send for rework, all right, to fix the faults. All right. So we work out the probability. It is 0.09. So it's quite bad. 9% of the door need to be reworked. Not very good. All right. So pass the inspection. Again, this is make it life easier for a particular door. Either it pass the inspection or fail the inspection. But if I want to make it more complicated, how to make it more complicated? I don't know, of course. So it's similar to I don't know. Yes, it passed, it fails, and somewhere in between. Not determined. All right? So in this case, I don't make it so complicated. So either pass or fail. So for example, okay, if we find two or more faults, we send for rework, fail inspection. But if we don't find any faults, then we pass and strip it out. So what happens if I find 1? Somewhere between 0 and 2. I will not decide. I may have to do something else. So in this case, when you find the number of faults equal to 1, then it's not fail, not pass. All right. So that is the undetermined one. All right. So usually we have to do further work on it. All right. But what I mean is that there may be a third possibility. But in this case, we just pass or fail. All right. Just like your exam, right? Either you pass or fail. Do we have a third alternative for the taking the module? Either you pass or fail, right? Any other choices? Is that incomplete? If you have valid reason, you may incomplete. So, not fail, not pass, but you don't get the credit. All right. So, but I just want you to be aware of that. Ask yourself, okay, in this example, we have fail and pass. So greater than 2 false, greater or equal to 2 false, fine, fail the inspection. But if it's less than 2, we pass it. All right. Okay. So now this is to link up what we just learned last week, all right, about binomial distribution and the Poisson distribution. So X is the number of successes. All right, it follows a binomial distribution with parameter n and p. All right, so this is the PDF. Sorry, the probability function. All right. Now, the number of successes in n trials. While Poisson is also number of successes, but over an interval. All right, but in fact, these two are sort of related in the sense that if your n is very large, don't be frightened by this. It simply says that n is very large, maybe 100, maybe 1,000, or maybe 10,000, for example. So the idea is like this. Remember we talked about Poisson experiment. If this is the interval, let's say within 1 hour, 0 to 1 hour, all right, I can divide this interval into many sub-intervals. All right, so for each sub-interval, all right, so we will have the following scenarios. Either there are no occurrence, or there are one occurrence. And the chance, because it's so small, the chance that you have 2 or more occurrence can be assumed to be 0 or negligible. What we use, the word we use is negligible. So what does it mean? It means that basically I divide this interval into n trials. Each one has only 2 outcomes, 0 or 1 occurrence. So it's like a binomial situation. So then we count the number of successes over this interval. It's the same as counting the number of successes over these n intervals. All right. Now, because the interval is so small, the chance of 1 occurrence there, all right, or the success, probability of success should be very small. So that's why if you have a large number of n for binomial, and if the p is very small, the probability of success is very small, then we can consider it as a Poisson experiment, and we can approximate it by Poisson distribution. So what Poisson? So it means that if this holds, then x, instead of follow a binomial with n and p, then we can consider x is approximately follow a Poisson distribution with a parameter lambda. Then what is this lambda? How does lambda related to n p? So it turns out mean. So what is the mean for binomial? The mean for binomial distribution is n times p. So Poisson with a parameter which is n times p. All right. So what I'm saying is that we try to link up the two distributions, binomial and Poisson. They are not the same. Only when your n is big and p is small for binomial distribution, then it behaves approximately like a Poisson distribution with the parameter equal to n times lambda. All right? Okay, so this is what it means. So here is an example. I think it's quite straightforward. So suppose a car has an accident. Accident here is considered as at a junction. I mean, accident at a junction is 0.001. And suppose there are 1,000 cars passing through this junction. So what's the chance that 2 or more occurrence during that period? So, all right. So in that, okay, so 1,000 cars pass through that period. So suppose there's a fixed period, and then we are asking, all right, so what is the chance that x is equal to, okay, so we can think of it, you have 1,000 cars, all right, 1,000 cars. So, okay, 1,000 cars. So basically the number of accidents occur follow a binomial distribution with 1,000, n equal to 1,000 and p equal to 0.001. All right. So the n is considered big and p is considered small. So this one you can consider as divide a particular interval of period into 1,000. Okay, it's not exactly like that, but then it fits to our theory that n is big, p is small. So the behavior, this what? N choose x, p to power, okay, 0.0001 of x times 0.99999 raised to power 1,000 minus x. All right, this one, to compute this, is the same as e to the power minus np. What's np? Np is this times this equal to 0.01. So it's 0.01 over x factorial. So these two are more or less the same. How do I get this 0.01? 0.01 is coming from n times p. That means 1,000 times 0.0001. All right? Am I right? Okay. So you may argue, okay, I have a very powerful calculator, I have a very powerful computer, I can compute this probability. Forget about the approximation. But what we're trying to do is that you understand how things are related. So Poisson distribution can be considered as, we call it the distribution that binomial or the asymptotic distribution of the binomial distribution if n is getting big and if p is small. All right, so here it is. So we calculate probability x greater or equal to 2. All right, so it's like that. So we can use the Poisson approximation, and hence we just have to calculate. You see, this one is much easier. All right. Then this one also easy, right? You think? Is it easy? 1 minus 1,000 to 0.000, 0, 1 to power 0.9999, 1,000, and then minus 1,000 choose 1, all right, 0.0001, 1, 0.9999, 999. All right, not that difficult. I think your calculator, ordinary calculator, is still able to do it. But then if I change this from 2 to 10, how to calculate this? Because you need, for example, I want this change to 10. So one of the terms you need to compute this one. Then by definition, in fact, it's 1,000 factorial over 10 factorial over 990 factorial. Can your calculator calculate 1,000 factorial? I doubt it. All right. Of course, if you twist a little bit, all right? Yes, I cannot do it, but I can cancel it before I do it. So this is 1,000 up to 991. Only 10 numbers. Your calculator can calculate the product of these 10 numbers. I hope not. All right. Then divide by 10 factorial. All right. But all this is sometimes it's quite hard to get. So that's why I need the approximation. So you can see that. If I do the approximation, then you can see that here. Even if I change probability of x equal to 10, then I just have to modify this 0.1 to power 10, and then this one is 10 factorial. So it's still manageable using ordinary calculator. All right. So I just want you to be aware of the objective of this approximation to link up the two things, as well as to look at it to ease your calculations. All right. Okay, I think I skipped the example 2. You can read it yourself. All right. Although I mentioned that in order to use this one, n has to be big. Okay. If you're afraid of this one, just large. So how large is large is up to you. 1,000 is considered quite big. And then p has to be small. Small means close to 0. But I think we used it before. You can also use it when n is large and p is large. Large means that it's close to 1. All right? So either p is very small or p is very big. Because p is big, you simply swap the definition of success and failure, then p becomes small. All right? So you can still use this Poisson approximation by properly swap the definition of success and failure. All right, so let's start the continuous uniform distribution, continuous distribution. So the first one, the easiest one, uniform distribution. Let me repeat again why we call it uniform. Uniform means that the probability density function will be the same so long as x is within the interval. In this case, a and b. So long as it's the same PDF, it does not depend on the value of x. So long as x lies between a and b, then they have the same. So you can see that this is the PDF. So long as x between a and b. And you can see that this one, this formula or the expression of the PDF does not depend on the value of x, so long as x is within A and B, and 0 otherwise. Then, of course, you have to know what is the expectation. Okay, sometimes this is referred to a rectangular distribution because it will be something like this, A and B. So the distribution will be like this. What is this height? This is the density function, 1 over B minus A, right? Because this is B minus A. So B minus A is the width, and 1 over B minus A is the height. So the area, this area, is 1. All right? So make sure it's 1. So I always stress that the PDF can be bigger than 1, because you think of it, if it's uniform between 0 and 0.5, then your PDF, this one must be 2, because this length is 0.5. 2 times 0.5 will give you this area equal to 1. Otherwise, it will be different from 1. So you can have a density which is bigger than 1. But not the probability function. For discrete case, the probability function cannot exceed 1. All right? Oh, so here's the graph. This is uniform between 3 and 7. Okay, the mean, you can easily work out. It is A plus B over 2, which is just the midpoint of the interval A and B. Right? This is A and B. So that the average or the expectation is somewhere between A and B. And the variance can be shown equal to B minus A squared over 12. All right? All right. So for the proof, it's just a very straightforward calculus or integration. So remember, to find the expectation of x, it is x times f of x. Then you're supposed to integrate from minus infinity to infinity. So that is how you get the expectation of x. Then, from minus infinity to a, the PDF is 0. So it's x times 0 dx plus a to b, x times 1 over b minus a dx plus b to infinity, again it's x times 0. So these terms are gone because the PDF is 0. I just want you to be aware of that. This, I keep telling you this. All right, so the integration separate into 3 because the PDF takes different form over different region. All right, so after you complete the integration, you get the answer a plus b over 2. Then get the expectation of x squared. All right, which turned out to be this one. All right. Just recall your algebra. All right, this one is equal to a or b minus a times b squared plus ab plus a squared. All right. I don't know whether I still remember this is your factorization. All right. And also, because variance of x equal to expectation of x squared minus the square of the expectation. So that's why we need to compute this one. And we work out. So the variance is equal to, after simplified, it is b minus a squared over 12. All right? Okay, so here is example. So we choose a point randomly in a line segment 0 to 2. Random means that it's equally likely at any point of 0, between 0 and 2. So this is described by uniform distribution. So you can think of it, x is the point where you land, or where you pick up this point. So what's the probability that the chosen point lies between 1 and 3 over 2? All right? So in other words, this is between 0 and 2. I want to know what is the chance that the point that you pick up is between 1 and 1.5. All right? So, I think maybe you intuitively know the answer. The answer is 1/4. But I want to formulate it using the continuous uniform distribution. So now I define the random variable x. X is the position from the origin, 0. Okay? So I identify this point. X is how far it is from 0. All right? So x is taken from within the interval from 0 to 2. Therefore, this value, the position, is uniform over 0 and 2. All right? So, and this is the PDF. All right? 1 over b minus a, so long as x is between a and b. So then we ask to find this probability, x between 1 and 2/3. So we integrate 1 to 1.5. And the PDF, this range, between 1, for x between 1 and 1.5, the PDF is equal to 1/2. So integrate 1/2, where x from 1 to 1.5. So the answer is 1/4. All right? Okay, here's another example. Find the CDF of the uniform distributed random variable between A and B. So in other words, just now we are asked to x follow uniform with 0 and 2, and then we are asked to find probability of x between 1 and 1.5. All right, so that's the previous example. Now we are having x follow uniform A between A and B, and we are asked to find the probability of x less or equal to x, little x. All right. So remember, to find this, the definition is integrate from minus infinity to x, f of, I change, I don't want to write x, otherwise I cannot tell the difference between the x here and the x here. They represent different things. So now I change it to t, the PDF, f of t. All right. Okay, so it's like that. Now, remember, f of x takes different form. So when x, all right, let's see, when x is less than a, then your PDF is 0. So when x is less than a, then the PDF is 0. So this answer is 0. When x is between a and b, then I have to separate this integration into two parts. One is integrate from minus infinity to a, f of t, dt, plus integrate from a to x, f of t, dt. But this one, within this interval, the PDF is 0. So you have this and this. And when x is bigger than b, then you have even add one more from b to x, f of t dt. All right? So this one is 0. This one is 1. And this one is 0. All right? So this is the answer. All right. So it is 0 when x less than a, is 1 when x is bigger than b. While in between, you have to complete the integration. It turns out it's x minus a over b minus a. All right, so that's the CDF. All right, so let's look at some more interesting distribution, continuous distribution. And this is a very, very common and very useful distribution called exponential distribution. The idea is that, okay, this is the PDF. It's like that, exponential decrease. Can it be like that? all the exponential distribution we talk about will be shaped like this. This one is not true unless you fixed this upper bound. It cannot be infinity, otherwise the area is infinity, right? So anyway, okay, so this is the PDF of the exponential distribution. So only cover the region X is positive. For negative, the probability density is 0. And it's in the form of a constant alpha times e to the power minus alpha x. So ask yourself, is this positive? This part, is it positive? Yes. Exponential function is positive. All right. E to the power anything is positive. And what is e to the power 0? 1. What is e to the power minus 1? Is that a negative number? No. So it's 1 over e. All right. So it's a positive number. All right. So you cannot have a negative number. All right. And then this one, so long as alpha is positive, then this whole thing is positive. So make sure that alpha is positive. All right. Then remember I mentioned you must link up the parameter, in this case is the alpha, with the something that we understand, like expectation of x or variance of x. So we can, this is another criteria that easily check will fulfill. And here is the expectation of x equal to 1 over alpha. That means this parameter that we defined is equal to 1 over, or take the reciprocal, is equal to expectation of x. And the variance is equal to the square of this one. So it's 1 over alpha squared. Now, a word of caution here. If you write down your PDF of exponential in this form, 1 over, let's say, 1 over mu e to the power minus x over mu. All right? If I write it in this form, then expectation of x is equal to mu, and variance of x is equal to mu squared. All right. So I want you to be aware of, depends on the form of the PDF. If it's written in this form that I gave you here, all right, then the expectation is equal to 1 over alpha. But if I write it like that, then you can show that expectation of x in fact equal to mu, equal to the parameter. All right. So in other words, it's a little confusing. Sometimes people use this way to represent a PDF of exponential. Sometimes they use the expression that I give in the previous slide. All right? But just remember, you must be able to link the parameter, the unknown, the constant in the PDF with the expectation. So that will guarantee that you will get the correct form. So if I define it like that, it means the expectation of x is equal to mu. If I define it like this, then the expectation is equal this f of x. If I define it like that, then expectation of x equal to 1 over alpha. 1 over alpha. All right. So here's the proof. So x times this one, and in fact, it's supposed to be from minus infinity to 0 f of x dx, x times f of x dx. But when x is within this range, f of x equal to 0. Therefore, you don't see this part. It looks as if you start from 0, but you must know that why we start from 0, because from integrate from minus infinity to 0, okay, x times the PDF, because the PDF is equal to 0 where x within the range 0 minus infinity to 0. So it's like that. All right. Then this part, okay, is obtained by differentiate this part. You differentiate this, you will get this. All right. You know how to differentiate this one? So differentiate this one with respect to x, you will get, all right, minus e to the power minus alpha x, and then differentiate this minus alpha x with respect to x. So you've got a minus alpha times this whole thing. So that's why it becomes alpha e to the power minus alpha x. All right? Revise how to do the integration or differentiation for exponential functions. All right? So I write it like that. Then apply something called integration by parts. Integration by parts saying that if you integrate v du, all right, in this case, this is my v, this is my u. Then it's equal to u times v minus u dv. All right? So it becomes product u and v. All right? Then minus integrate. All right. Integrate from 0 to infinity. This becomes here, and this becomes here. So it's just like ordinary integration. All right. So integrate this one, gives you 1 over alpha. All right? Okay. Then we work out similarly for expectation of x squared. So this time you can see that now I repeat what we did in the previous slide. So this time, so this is u times v, right? And then minus v du. But this one is dx squared, so I have to write it, I have to differentiate it. This becomes 2x dx. All right, 2x dx. So in other words, this becomes integrate, all right, minus 2x e minus alpha x dx. All right. Okay. Oh. Something wrong, right? Because differentiate this one, sorry, and there's alpha here, I'm sorry. Nothing wrong. Okay, so here, but then, all right, so when we come from here to here, so we're 2, and then why I have to do such thing? This one cancel out, but why I have to write it like that? Why? Can I just integrate 2x e to the power minus alpha x dx? Why I have to take out the 2 here and then put alpha here and put alpha here? Why? Does this look familiar? Yeah. One copy from previous one. We have already done it. This is expectation of x. So this is this equal to 1 over alpha. All right? So without this one, what is it? 1 or this is integrate the PDF. So now with x, then it is expectation of x, which we have already done it. All right? How about x squared? We have not done it. We have to do it now. But now I got the answer. This is the answer. So from now on, I even know integrate x squared alpha e to the power minus alpha x dx from 0 to infinity. So this, I would say that is equal to 2 over alpha squared. All right? So what I mean is that you have to make use of what we just did. So we have already got the expectation of x when x follow exponential. Check with the sign, some negative sign may be missing, so you have to put it right. There may be some typos here, all right? But anyway, the answer is correct. That's pretty sure. All right, so the variance of x equal to expectation of x squared minus the square of expectation, so equal to 1 over alpha squared. All right? So, yeah, this is what I just mentioned earlier. So if you write it in this form, then this is the expectation and this is the variance. Wow. Now, exponential distribution have this no memory property. All right? It's only this this exponential distribution has this property. All right? So, what does it mean? Okay, if x follow exponential distributions with alpha bigger than 0, all right? And if you have two constants, two numbers, positive number s and t, then what does this mean? This means that given that this exponential random variable is greater than s, then what is the chance that this random variable is greater than s plus t? All right? Then it says that it's equal to probability of x greater than t. To some of you may be very natural, but in fact it's not true in general. Only true for exponential distribution. All right? What it means is that, okay, when we say no memory, what does it mean? It means that we don't care whether, so long as it is x is bigger than s, then you ask what's the chance that it's bigger than s plus t, equal t more. All right? Then you say that, okay, it doesn't matter what your s is. It's the same as if you start fresh. The chance of x, okay, greater than t. So in other words, all right, 0 s t. All right? So the probability of knowing that we are already here, all right, x already bigger than s. What is the chance that it is big for, the x is bigger than s plus t? So, sorry. This is s plus t. So this is t, this is s, all right? This is s, this is t. So this is s plus t. So given that you are already here, already bigger than s already, so what's the chance that it's bigger than s plus t? So the probability is the same as if you start here as fresh. Go beyond t. Go beyond that. All right? So this is what it means. X greater than t. All right? So, okay, I think I explained it. Give you some interpretation. It looks as if like this. The bus arriving time can be modeled by exponential distribution. So you can think of it like this. Someone has already waiting at the bus stop, waiting for, let's say, 10 minutes. Then what's the chance that he waits another 5 more minutes? Given that he's already wait, all right, 10 minutes. What's the chance that he waits another 5 minutes? That means altogether 10 plus 5 minutes. So as it looks as if you just arrived here. You just forget about he has waited for 10 minutes. So what's the chance that he wait for 5 minutes for the bus to come? More than 5 minutes for the bus to come. Let me repeat it. Say it again, okay? So the bus stop there, okay? So if I go, I'm at the bus stop and already waiting for 10 minutes already. So I want to know what's the chance that I have to wait altogether 15 minutes. All right? Given that I've already waited for 10 minutes already. All right, what's the chance that I wait for more than 15 minutes? So it's the same as another guy or might just come at this 10 minutes point in time. How long he waits? What's the chance that he waits more than 5 minutes? So it's the same as me, because although I wait for 10 minutes, but I want to ask what's the chance I wait for 15 minutes. So it's the same as a guy just come here and wait for 5 minutes, more than 5 minutes. All right. So that's how to interpret this no memorous. So it doesn't matter whether how long you wait. It's the same as you just start fresh. You have to wait. The time t. In fact, why I say that is only applied to exponential. You can prove that. All right. So I want to work out this probability. This is a good exercise. It's probability of two events. Probability of event A given event B. What is event A? Event A is x bigger than s plus t. Event B is x bigger than s. So if the event A intercept event B, divide by probability of event B. All right? It's what we learned in chapter 2, right? Chapter 1. All right, then, what is the intersection of this one? One event is x bigger or equal to s plus t. The other is s bigger than s. All right? Is this a subset of the other one? Which one is a bigger set? If I call this A. So A a subset of B, or B is a subset of A, or A and B has nothing in common. Or not common, not one included in the other. What I mean is that whether this is A, this is B, or whether this is B, this is A, or whether this is A, this is B. Look at A and B. Which one is the bigger set? A, ask you x bigger than 10, and ask you x bigger than 10 plus 5. Which one is bigger? X bigger than 15, right, is a smaller set. It does not cover x equal to 10, equal to 11, but x bigger than 10 cover any number between 10 and 15. So this is a bigger set. So A is a subset of B. So A intercept B is equal to A, so equal to A. All right? All right? So we do the integration. All right? From s plus t to infinity, this from s to infinity. And after you do the integration, it turns out to be like that. Then, can I cancel this one with this one? And this becomes 0? Don't make such mistakes, huh? This numerator is alpha s times e alpha t. So this cancel with this, you're left with e power minus alpha t, which is the probability of x greater than t. Remember, x is exponential with parameter alpha. And the PDF is given by e to power alpha e to power minus alpha x for x greater than 0. And the PDF can be shown, okay, you can work it yourself. It's 1 minus e to power minus alpha x for x greater than 0. This is the CDF. All right. So it's just an exercise to prove that the conditional probability is equal to the probability of x greater than t. And we call this property no memory or memoryless property. And this applies to exponential distribution. Okay, so I try to show you this. Okay, so you can think of it, x denotes the life length of a bulb. Okay, it is the lifetime of a light bulb, and given that the light bulb lasts s time units or s days, then this is x greater than s. So now we ask, so what is the chance that it will last in the next t days? All right, so now we ask, what is the chance that x is greater than s plus t? So this will be the same as the probability that it will last for t units as it was new. So it looks funny. I already used it for S days and then still look like new one. It does not look like a new one. But then the probability of that it lasts another t days or t units is the same as if it is just start from fresh. All right? This is assuming that the lifetime of this light bulb follow an exponential distribution. All right. Okay, so here's an example. Find the CDF. So you work it out yourself. All right. Just remind you once more. This does not equal to this. We skip one step. It is from minus infinity to 0 and 0 dt plus from 0 to x f of t dt. All right. So this one is 0. So that's why you don't see it. All right. So then you do the integration. So after you got this one, you substitute x. So you have minus e to the power minus alpha x. And then minus, substitute 0. So it's minus e to the power minus alpha times 0. And this one is equal to, this one is equal to 1. So plus, minus minus becomes plus. So it's 1 minus e to the power minus alpha x. And this is only valid for x greater or equal to 0. Then what happens if x is less than 0? X less than 0, you have this. This is replaced. The PDF is 0 when x is less than 0. All right? So in that case, the CDF equal to 0. All right? So it's only this one. When x bigger than 0, you have this expression. Otherwise, it is 0. Okay, suppose the failure time, which represented by this random variable t, is exponential distributed with mean 5. So immediately, if you want to express your PDF, so the PDF is equal to 1 over 5 e to the power minus 1 over 5 times, right, times t, when t is bigger than 0. All right, what's the probability that at least 2 out of 5 of these systems are still functioning at the end of 8 years? All right. Now, we are asked the probability. But the probability is not on t, but on the number of systems that still function. All right, wow, it looks very complicated, but you can think of it, the number of systems out of 5 systems, or out of 5 components. Number of successes out of 5 trials. Think of it like this. Whether it's still functioning or not. Functioning at the end of 8 years. If it's still functioning, consider success. If it fails, then it's considered failure. So basically, the probability that you are asked to compute is probability of the number of successes is at least 2. All right? Out of 5 trials. So, you can think of it, Y is the number of systems, number of successes out of 5 trials. 5, each trial is considered, each system is considered a trial. And there are only success or failure. Success means that it lasts, it works at the end of 8 years. All right? So Y is a number of successes, so it follows a binomial, and 5, and the probability P. And what is this P? It's the probability of success. A success, we define it as it's still functioning. This is considered as a success. All right? So what is the probability that it still works at the end of 8 years? So that means the lifetime, or the failure time, all right, is is what? How this link to x equal to x, less than x, greater than x. We are talking about failure time now. Right? It fails. So it follows an exponential distribution. So it's greater than or less than. I want it still functioning at the end of 8 years. So, okay, ask you, if I put less than 8, what does it mean? It means it fails before 8 years. Is it what we want? No, right? Is it? Okay, let me repeat. If I put a less than, what does it mean? It means that it fails, all right? Failure time is less than 8, right? So now I want the failure time bigger than 8, right? So that it's still working so hard, even after 8 years, all right? So we want to have probability of t greater than 8. All right? So in this question, it's not directly ask you what's the probability of t, but instead, you are working on a random variable which follow a binomial distribution, but you have to work out the probability of success. All right? So the probability of success is about 0.2. I take approximation, it's easier for us to compute the binomial distribution. So the binomial, x follow binomial distribution with n equal to 5 and p equal to 0.2. So we are asked what is the chance that it's greater or equal to 2. More, at least 2, that means it's greater or equal to 2, and the probability is 0.2827. You can use this command in Excel, exponential.dst, to get the distribution. All right. 3 parameters, x, in this case is 2. All right. Lambda, which is equal to 1 over the mean, or 1 over 5 in this case. And this, if it's true, give you the probability, if this is true, it gives you the probability of x less or equal to x. If it's false, then it gives you, it's not cumulative, then what it gives you is equal to that probability. All right? Okay. Okay. So this one, again, is quite straightforward, so I leave it to you to read it. All right. We'll continue Thursday, this one. All right. So we stop here. Oh, 1 page only. Okay, sorry, just a few lines. Exponential distribution can be used to model the distribution of the time between occurrence of 2 successive events. This is an event occur, this is another event occur. So we can model this, when is the next time, the time between this event occurrence and this occurrence. So we can model by exponential. It's very obvious, right? Remember these memorous properties. So this is what happened. So I don't care about what happened. So at this time point, what's the next occurrence? So it looks as if I look at how long it takes for the next occurrence. So this can be used, or the exponential distribution can be used to approximate the time to take for the successive occurrence. All right. So that's another way to use the exponential to model the time taken between 2 consecutive occurrences. So how long it takes. So this time follows the exponential distribution. Okay, sorry about that. I didn't know that that's the only last page. Okay, and the next lecture will talk about normal distribution, our familiar distribution.